Snap your fingers, and in that sliver of a second, a beam of light could circle Earth 7 times. 7 laps around a whole planet, faster than a blink can finish forming. 292, 628, 458 metri per secondo. The fastest thing we know, the hard ceiling of reality, the gold standard we worship and chase. But here's the truth most people never sit with. On the scale of the cosmos, the speed of light isn't fast. It's agonizingly, tragically, terrifyingly slow, like a snail crossing a continent. Out there, even instant has weight, and every second feels like a long hallway with no doors. And the light year, the number we toss around so casually, isn't a unit of exploration. It's the thickness of the prison wall around us. The sun you're seeing right now is already 8 minutes in the past. If it vanished this instant, you wouldn't know for 8 minutes and 20 seconds. You'd finish your coffee, kiss your child, worry about your taxes, while orbiting a star that no longer exists. Mars is minutes away at light speed, and still, that delay can be fatal. An astronaut screaming for help might wait, and the answer would arrive to a silence. The nearest star is over 4 years away at light speed, and about 73,000 years away at the pace of our fastest rockets. The far side of our galaxy is roughly 100,000 light years distant. The light arriving from there tonight shows a Milky Way that existed before humans did. We are, in a very real sense, prisoners a cage built from physics itself, and the bars feel tighter as space expands beyond our reach. Can we escape, or are we destined to die on this rock? Staring at stars we can never touch. Chapter 1. The Illusion of Instant. But before we begin, don't forget to subscribe. And if you truly enjoy these videos, please leave a like. Let's begin. Snap your fingers, and in that brief click of sound traveling from your hand to your ear, light could have looped around Earth 7 times. 7 full circuits around a planet, nearly 40,000 kilometers around. To creatures made of flesh and breath, to minds that measure speed in footsteps and heartbeats, light feels like magic. It feels immediate, like thought itself. It is the cosmic speed limit stitched into the fabric of reality. 292, 628, 458 meters per second. That is the number exact, not approximate, because in 1983, we defined the meter by the speed of light. The distance light travels in 1/299, 628, 458 of a second. Light stopped being something we merely measured. It became the ruler we used to measure everything else. For centuries, humanity has treated this speed like a holy constant. We push information through fiber optic cables at nearly this velocity. We design chips knowing even electrical signals creep compared to it. We dream of starships that might someday approach this barrier. We look up and think, if only we could go that fast, the universe would open. It's a beautiful thought. And it's also a lie we tell ourselves to sleep easier, because we're about to dismantle your sense of fast, step by step, measurement by measurement. We'll see that on cosmic scales. Light is not swift. It is painfully slow, a snail on a continent, a glacier easing down a valley, molasses in deep winter. And the light year the distance light travels in 1 year is not a measure of how far we explore. It's the thickness of the walls around us. Every light year between us and another star is 1 full year of travel at the fastest speed physics allows. Every light year is a gap that quietly mocks ambition. Consider the sun, that roaring sphere of fusion that rules our sky, warming your skin, making life possible. It feels present. You step outside, feel the heat, and your mind says, it's right there. But it isn't right there in time. The light touching your eyes left the sun 8 minutes and 20 seconds ago. You are not seeing the sun as it is. You are seeing a ghost where it was. If some impossible force erased it in this instant, you still wouldn't know. For 8 minutes and 20 seconds, the sky would stay blue. Flowers would keep drinking photons. And gravity, its changes traveling at light speed too, would keep Earth in its familiar curve. You'd finish your coffee, check your phone, dread the meeting later. And then, without warning, darkness would arrive, the temperature would begin to fall, and Earth, freed from its tether, would drift into the void like a stone released from a sling. That 8-minute delay is the first crack in how we imagine reality. It's our first hint we are not connected to now. We don't live in the present tense of the universe. We live in its recent past. Every photon that reaches you is already history. But 8 minutes is still digestible. A coffee break, a microwave timer, a small mercy. So let's step farther out. Let's leave the warm familiarity of our star and reach for the next rung of our ambition. Let's go to Mars. Mars, the dream we've covered with robotic tracks, the world we promise ourselves will one day stand on. We talk about becoming multiplanetary. We imagine domes and gardens under glass, terraforming sketches, networks stretched between worlds. Rockets rise, plans gather, and yet we forget the lag, the quiet, lethal delay built into space. At closest approach, Mars is about 3 light minutes away. At farthest, more than 22 light minutes. Now picture yourself there, boots in red dust. A thin pink sky overhead and something goes wrong. A seal fails. An alarm shrieks. Atmosphere is venting. You have minutes. You shout into the radio, Houston, we have a problem. Your voice becomes radio waves, light-speed information, and still it takes 20 minutes to reach Earth. In Houston, someone is sipping coffee. They hear your panic 20 minutes after it began. They answer immediately, step-by-step instructions launched at the fastest speed the universe permits. Another 20 minutes to return. 40 minutes total. You are already gone. Light speed didn't save you. Light speed killed you by making rescue arrive as a memory. This is what science fiction often softens. There is no real conversation in deep space. Only echoes, only history, messages like bottles tossed into a black ocean, hoping they arrive in time. Now consider Voyager 1. Launched in 1977, the fastest thing humans have ever built. Nearly 50 years of flight. Racing at about 61 kilometers per hour, past the planets, beyond the solar wind, into interstellar dark. And measured against light, it's almost motionless. Voyager 1 is only about 22 light hours away. Not light years, light hours. It hasn't even reached a single light day. And the solar system's far frontier, the Oort cloud. That great sphere of icy debris may stretch out to nearly 1 light-year from the sun. Light itself takes a full year to cross our cosmic neighborhood. Aim a flashlight toward that edge today, and you'd wait 12 months for the beam to arrive. Seasons would turn. Holidays would pass. A year of your life would slip by while the fastest thing in existence crawled toward the boundary of home. Beyond that edge, the true abyss. And in that darkness, Alpha Centauri waits at catch. 24 light years. 4 years and a few months at the absolute limit just to reach the nearest neighbor. Shrink the scale, make the sun a grain of sand. Earth a speck 3 centimeters away. Then Alpha Centauri is another grain of sand, 30 kilometers distant. And between them nothing. A long, empty howl of space. We are not sailors skipping between islands. We are castaways on a pebble in a sea so vast it borders on the infinite. Even a ship at the maximum speed nature allows would take more than 4 years to reach the nearest shore. The speed of light is not fast enough. Not for bodies that live briefly, not for civilizations that blink on cosmic timescales. And we haven't even left the neighborhood. The galaxy awaits. The universe awaits vast beyond what the human mind can truly hold. To understand how we learned this, we go back. Back to a time when people didn't even know light had a speed. Back to 1676, to a Danish astronomer watching Jupiter's moons, about to measure the unmeasurable. And change everything. Chapter 2, the first measurement. For most of human history, light was assumed instantaneous. The Greeks argued. Aristotle treated light as a kind of presence, not a traveling thing. Others guessed it might be finite without proof. The debate floated free of experiment. In the early 1600s, Galileo tried to pin it down. 2 observers on hilltops, a known distance apart, each holding a shuttered lantern. One uncovers his light. When the other sees it, he uncovers his in response. Measure the delay, calculate the speed. It failed not in idea, but in scale, even at 10 kilometers apart. The round-trip travel time is only about 66 microseconds. Human reflexes are oceans too slow. Galileo could only conclude if light has a speed. It is extraordinarily fast. He guessed it might be 10 times faster than sound off by roughly a million. The breakthrough came indirectly, from navigation and clocks and careful patience. Ole Rømer, born in Denmark in 1644, grew up as astronomy sharpened into mathematics. Tycho Brahe built the most precise observations of his age. Kepler extracted laws of planetary motion. Galileo discovered Jupiter's 4 moons, and those moons, especially Io, became a cosmic clockwork worth studying. Io, fast and faithful, orbits Jupiter every 5 hours. Galileo suggested its eclipses could serve as a universal clock time, an eclipse from your location. Compare it to prediction. Determine longitude. For sailors losing ships to uncertainty, this mattered. Rømer arrived at the Paris Observatory in 1671 to refine those eclipse predictions. He wasn't hunting for light speed. He was hunting for accuracy. And then he saw a pattern that shouldn't have been there. The eclipses drifted. When Earth moved toward Jupiter, eclipses arrived earlier than predicted. When Earth moved away, they arrived late. Small differences, yet persistent. Measurable. Over 6 months, the accumulated discrepancy grew to about 22 minutes. Io wasn't misbehaving, so the cause had to be elsewhere, something between Jupiter and Earth. Then the idea landed. Quietly and perfectly distant. When Earth was closer, the eclipse light had less space to cross. It arrived sooner. When Earth was farther, the light had to traverse the extra width of Earth's orbit. It arrived later. The timing wasn't noise. It was a clock measuring how long light took to cross the diameter of Earth's orbit. On November 21st, Rømer presented the argument. He predicted a specific Io eclipse would be 10 minutes late, and it was. The world had to accept it. Light needs time to travel. Rømer estimated 22 minutes to cross Earth's orbital diameter. Christian Huygens used that estimate and the best orbital measurements available to calculate roughly 220 kilometer z, the first human measurement of light speed. The number was off. The true value is close to 300, 0 kilometers per second, but the concept was revolutionary and correct. The error came from imperfect orbital knowledge and an overestimate of the delay. The real crossing time is closer to 5 minutes, and Earth's orbital diameter wasn't precisely known then, but the insight endured. Light is finite. Not infinite, fast beyond intuition, yet not instantaneous, and that finitude can be measured. 2 centuries would pass before all implications sank in. If light takes time, we never see the universe as it is. We see it as it was. Farther distance means older images. The sun appears 8 minutes old. Stars appear years old. Galaxies appear millions of years old. The universe is not a snapshot, it is a layered archive. A sky full of time. Every direction you look backward. But Rømer's result also raised a haunting question, answered only in 1905. If light has a speed, what does it move through? Sound needs air. Waves need water. So physicists imagined a medium, the luminiferous ether, an invisible substance filling all space. Light, they said, was a wave in this ether. It seemed reasonable, because waves needed something to ripple through. But the ether idea made a prediction if Earth moves through the ether. Light speed should differ by direction, faster downstream, slower upstream, like a boat in a current. In 1887, Albert Michelson and Edward Morley built an exquisitely sensitive experiment to detect that difference. They measured light speed in different directions, across seasons. As Earth moved through space, they found nothing. No ether wind, no directional change. Light moved at the same speed in every direction, always. Physicists were stunned. It clashed with common sense. On a moving train, throw a ball forward, and a person on the ground sees the speeds add. That's how everyday motion works. But light refused to add. Turn on a flashlight on the train, and the beam doesn't go c plus the train. It goes at c. Period. Source motion doesn't matter. Some tried to save the ether with mathematics. Hendrik Lorentz and Henri Poincaré developed transformations that could preserve the results clever, powerful, but increasingly like patches on a cracking hull. The deeper answer came from a young patent clerk in Switzerland, a man without a laboratory, but with a mind full of imagined worlds. Albert Einstein, 26 years old, about to overturn centuries with two postulates and relentless logic. The year was 1905, Einstein's miracle year. That September, he published a paper that would reshape our understanding of light and of space and time themselves. Chapter 3: Einstein and the Absolute Limit. Einstein wasn't the era's typical academic. After graduating from the Swiss Federal Polytechnic, he struggled for a university post. He tutored, taught, and finally worked at the patent office in Bern, respectable, but not prestigious. Yet he had something more valuable than equipment thought experiments. He could build a universe inside his mind, set the rules, and watch what must follow. Since 16, one question haunted him. What would you see if you could chase a beam of light? Run alongside it, match its speed. Exactly what happens. Classical physics suggested you'd see a frozen wave, an electromagnetic ripple suspended in place. But Maxwell's equations wouldn't allow such a thing. Light is an electromagnetic wave, and Maxwell's framework has no stopped light. A stationary electromagnetic wave wouldn't be light at all. So, either Maxwell was wrong, or our idea of motion was. Einstein chose the second. In 1905, he published On the Electrodynamics of Moving Bodies in Annalen der Physik. The paper was startling, almost no references. No new experiments, just logic, driven from two postulates. First, the principle of relativity. The laws of physics are the same for all observers moving at constant velocity relative to one another. In a smooth, windowless train, no experiment tells you whether you're moving or still. All inertial frames are equivalent. Second, the constancy of light speed. Light in a vacuum always travels at the same speed regardless of the motion of the source or the observer. Stand still. Run toward it. To fly away at half-light speed, you still measure 299. 792 km per seconde as it passes. Simple statements, with explosive consequences. Together, they shatter the Newtonian picture that had reigned for centuries. Because if both observers must measure the same light speed, something else must give. Imagine a train passing a platform. A passenger shines a flashlight forward. The platform observer measures c. The passenger measures c. How can both be right? Because they're using different clocks and different rulers. Space and time themselves adjust between moving observers. To keep constant, time must slow for the moving frame-time dilation. Not illusion, not error. Reality. Moving clocks tick more slowly, and lengths contract along the direction of motion, length contraction. A fast-moving meter stick is physically shorter to you than one at rest. Again, not appearance, but physics. At everyday speeds, the effect is tiny, undetectable at highway velocity. But as you approach c, it becomes dramatic. At 90% of light speed, time slows to less than half. At Noah's Edge, she Noah ascent. It slows to about 1/7. At Noah's Edge, she Noah, Bifinger Joe, about 1/22. And here the prison bars come into view. As you accelerate toward light speed, the energy required to keep accelerating rises brutally. The faster you go, the harder it becomes to go faster. Approach Ceph, and the required energy climbs toward infinity. At 90% of c, the effective resistance to acceleration has more than doubled. At Noah's Edge, she Noah percent, it's about sevenfold. At Noah's Edge, she Noah, Bifinger Joe, over 20-fold. To reach c itself would demand infinite energy and impossible payment. Therefore, nothing with mass can ever reach the speed of light. Not because we lack better engines, not because our fuel is poor, Because space-time is built that way. The speed of light is the speed limit of causality the fastest news can travel. It's the speed massless things must travel light. Electromagnetic radiation, gravitational waves. It's stitched into space-time structure. From this came the famous equation, E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy are interchangeable. Matter is energy held in a quiet shape. Energy is matter set free, because C is enormous. Even a little mass contains staggering energy, why nuclear weapons devastate, why stars burn for billions of years. And it also tells you why faster-than-light travel is forbidden to accelerate mass to C would require infinite energy. And the universe doesn't offer infinity. In 1915, Einstein expanded this into general relativity. Mass and energy curve spacetime, and gravity is the motion along that curvature. Light follows those bends. Time slows in strong gravity, and no information, not even gravity's influence, propagates faster than light. That last point matters. Gravity travels at c. If the sun vanished, Earth would continue its orbit for 8 minutes and 20 seconds before the change reached us. Not because gravity is slower than light, but because gravity is just as fast. And no faster. We are prisoners not only of distance, but of causality. We cannot know events before light can bring the message. We cannot act on distant places before light can carry our influence. We are islands of awareness in a universe where C draws the borders of the knowable. By 1915, the framework was complete. Nothing can exceed C. Nothing with mass can even reach it. And that speed, unimaginably fast in human terms, is agonizingly slow across cosmic distances. Now let's turn outward. Let's look at our solar system and watch the prison of light speed show itself in our own backyard, in minutes, in hours, in the quiet tyranny of delay. Let's count the light minutes that separate neighbors and understand why any spacefaring civilization must live with distance. Chapter 4. The Solar System Delay. We'll measure not in miles or kilometers, but in what truly matters, light time. The sun sits at the center, blazing, heavy, relentless, releasing about 3.8 watts. More energy in a second than our entire civilization has used across recorded history. And still, it takes time to arrive. From sun to earth, 8 minutes and 20 seconds. That is our baseline. You have never seen the sun right now. Only its recent past, always. Without exception. Mercury comes next, scorched and frozen. Year only 88 Earth days long. At closest approach, about 3 light minutes from Earth. At farthest, about 13 light minutes. A message out and back, 6 to 26 minutes. Venus follows Earth's twin in size, but not in kindness. Acid clouds, crushing pressure, heat that could melt lead. Venus ranges from roughly 2 to 15 light minutes away, at best. A round trip is around 4 minutes, and at conjunction, the sun blocks the path entirely. Then Mars, our obsession. Our next promise. At closest, about 3 light minutes. At farthest, more than 22. On average, roughly 12. So for astronauts, communication becomes something like slow email. Not a call. A message takes 3 to 22 minutes, one way. A reply takes the same. Ask a question at breakfast, get the answer at lunch, dinner, or tomorrow. Every decision needing Earth's input carries a built-in delay, 6 minutes minimum, 44 at maximum. In emergencies, that delay can kill. Fire, illness, structural failure. Astronauts will have to act alone, trained to be autonomous, carrying the skills of mission control inside themselves. Mars settlers won't feel like visitors with a lifeline home. They'll feel like pioneers at the edge of silence. Beyond Mars lies the asteroid belt, thin, wide, and mostly empty. Ceres averages about 17 light minutes away, with the belt spanning roughly 10 to 30 light minutes depending on geometry. Jupiter dominates the outer system, 11 Earth diameters wide, more massive than all other planets combined. Its gravity shapes everything, flinging comets, herding debris. Sculpting orbits. At closest, Jupiter is about 33 light-minutes away. At farthest, about 53. Round-trip delays become an hour or more. The Galileo spacecraft lived with that command. Wait. Confirm. Wait again. Saturn floats farther still, about 66 to 91 light-minutes away. Up to an hour and a half. Cassini couldn't be driven in real time. Controllers sent sequences and trusted the machine to carry them out. Uranus and Neptune drift in deep cold. Uranus, roughly 5 light hours at closest. Neptune around 4 light hours. When Voyager 2 reached Neptune in 1989, its images took over 4 hours to arrive, history traveling at the maximum speed allowed. Pluto, still distant no matter what we call it, was about 5 light hours away during New Horizons' 2015 flyby. The We Survive signal took 5 hours to reach Earth. Scientists waited helplessly, while photons crawled through the dark. Beyond Pluto stretches the Kuiper Belt. Then the far-flung Oort cloud, possibly trillions of icy bodies. The inner Oort may begin around 2000 AU, about 11 light days. The outer edge might reach 50,000 AU, or more, nearly a light year from the Sun. A light year of debris. Cold and quiet. Voyager 1, our fastest emissary, won't reach the inner cloud for roughly 300 years. It won't clear the outer edge for around 30,000 years. And even then, it will still be nowhere near another star. This is our backyard. Light minutes to hours across the inner system. Light days across the outer suburbs. Nearly a light year to span the full reach of home. Every deep mission runs on store and forward send. Wait. Execute. Wait. Receive. Wait. It is slow. It is meticulous. It demands patience, planning, and machines intelligent enough to survive without immediate help, because help is always minutes or hours away. For human exploration, the implications are stark. To journey to the outer planets is to journey into isolation beyond real-time support, beyond quick rescue, beyond comforting immediacy. A crew bound for Jupiter would need to be self-sufficient in ways no mission has required before their own mission control, their own doctors, their own engineers. They would send messages into the dark, then wait and learn to live inside the delay. They would have to be their own mission control, their own doctors, their own engineers. They would have to meet every crisis with only what was already aboard the ship, no resupply, no rescue, no second chance drifting in from home. By the time Earth even heard that something had gone wrong, the crew would have fixed it, or they would be gone, and Jupiter is still inside our solar system, still part of our close-by neighborhood. The stars are something else entirely, almost unthinkably farther. The nearest of them, Proxima Centauri, 24 light-years away, would still demand more than 4 years of travel even at light speed. At the pace of our fastest spacecraft, it would take over 70,000 years. But before we reach for the stars, we should understand what stretches between them, and how silence itself becomes a kind of distance. We should grasp the real character of interstellar space. Let us look into that darkness and notice how vast, how empty, and how quietly hostile it truly is. Chapter 5, The Interstellar Void. Breathe in, because this chapter is mostly silence. Imagine shrinking the sun down to a single grain of sand, a tiny yellow pinprick resting on a tabletop before you, warm only in memory. At that scale, Earth becomes a microscopic mote of dust, barely visible even through magnification, circling only about 3 centimeters away. Jupiter, the giant of the planets, it would be a small smear of powder, perhaps 30 centimeters out. Neptune would hover nearly a meter away, a faint fleck lost in the dim. And then comes the question that reveals the real dread of interstellar distance in this tabletop solar system. With the Sun as a grain of sand, where is the nearest star? Proxima Centauri, the closest stellar neighbor, would be another grain of sand, sitting about 30 kilometers away. 30 kilometers of nothing between 2 grains of sand. Place your model sun in the middle of London, and the nearest star would land somewhere near Oxford. Set it in Manhattan, and the next grain would lie beyond Philadelphia. And between those two specks there is nothing. No planets. No asteroids. No comets. Only a howling vacuum. Near absolute zero. Almost perfectly empty. The material out there is so thin that you could glide through a cube of space 100 kilometers on each side and meet only a handful of atoms, mostly hydrogen, with traces of helium and a whisper of cosmic dust scattered through a volume larger than many countries. This is the void. In fact, a single, quiet breath holds more atoms than you would meet in miles of that interstellar darkness. This is what stands between us and every other star in the galaxy, not an ocean to sail, not a desert to cross, but an abyss so vacant it strains the mind, and so cold it feels like time has frozen. Proxima Centauri is Patru, 24 light-years away, which means a beam of light moving at 300,000 kilometers per second needs about 4 years and 3 months to arrive. Light leaving Proxima Centauri today would not reach Earth until sometime in 2030, depending on when you are listening. Any signal we send, any message, any call into the dark takes more than 4 years to get there, and more than 4 years for an answer to return, as if every word must walk the long way through night. The fastest possible round-trip conversation with our nearest stellar neighbor is about 8.5 years. Sit with what that means. The universe demands patience from every traveler, and from every listener, as if time itself were thicker out here. If intelligent beings lived around Proxima Centauri and were waiting, our words would have to be worth a near decade of silence. Hello, we exist. 8.5 years later, hello, we exist too. How are you? 8.5 years later, we are well. How are you? Even small politeness would stretch into a quarter century. A real conversation would outlive generations, and Proxima Centauri is the closest. The Alpha Centauri system, of which Proxima is a distant companion, includes 2 other stars, Alpha Centauri A and B, slightly farther at 37 light-years. Past that, the numbers only climb. Barnard's star is about 6 light-years away. Wolf 359 is 7. Joe Lalande 12185 is 8. San Sirius, the brightest star in our night sky, is 6 light-years away. When you look at Sirius tonight, you are watching light that left while your children were toddlers or before they were born. You are watching the past arrive late, delivered by the slow inevitability of light across the emptiness, a delayed postcard stamped with starlight. Within 10 light-years of the Sun, there are roughly a dozen star systems. Within 20 light-years, perhaps 100. Within 100 light-years, tens of thousands each, one separated from us by years of travel, even at the fastest speed the universe allows. Each one sealed off by the prison of light speed. So, how long would it take to actually go? Start with Voyager 1, the fastest object humanity has ever sent on an escape path out of the solar system. Voyager 1 moves at about 17 kilometers per second relative to the Sun, roughly 61. 0.000 kilometers an hour. At that pace, Voyager 1 would need about 73,000 years to reach Proxima Centauri, crossing a gulf where nothing waits to welcome it. 73,000 years. Modern humans appeared in Africa roughly 300,000 years ago. The oldest known cave paintings are about 64,000 years old. Agriculture arrived around 12,000 years ago, and writing about 5. Ling ling ling. If we had launched a probe toward the nearest star back when humans painted bison on cave walls in France, that probe would still be sailing outward today. It would not be there yet. It would not arrive for another 9,000 years. At Voyager speed, Sirius would take more than 140,000 years. A star 100 light-years away would demand nearly 2 million years. By the time such a mission finished, our species might have evolved into something unrecognizable or vanished entirely. Even if we could build far faster craft, the timescales remain intimidating. Picture a ship that can cruise at 1% of the speed of light, far beyond what we can do now, demanding energy sources we have not invented and propulsion we can barely imagine. But let us allow ourselves this quiet miracle of engineering. At 1% of light speed 30,000 kilometers per second, the trip to Proxima Centauri would still take 424 years. Longer than any human empire has endured, longer than the entire history of the United States. Repeated several times. What about 10% of light speed? Now we step into science fiction, a ship racing at 30 million meters per second. The kinetic energy of even a modest 1,000-ton vessel would rival multiple nuclear weapons. The challenges become immense. You would need shielding for interstellar dust, because at those speeds even a grain becomes a bullet. Striking like constant machine gun fire, you would need to slow down at the destination, spending as much energy to brake as you did to accelerate. And you would have to navigate a darkness where the nearest landmark is still years away, with only instruments and perhaps an onboard mind of silicon to keep you steady. Even at 10% of light speed, the journey to Proxima Centauri would take 42 years. Someone could leave young and arrive old. Children born in transit could open their eyes under a new star, but the travelers would abandon everyone and everything they had ever known. They would reach a world where friends and family had aged by the same 4 decades. Yet there would have been no true conversation along the way, each message home taking over 4 years to arrive, and over 4 years more to be answered. At 50% of light speed, still beyond anything we can realistically build, Proxima Centauri would be 8.5 years away. At 90% of light speed, about 7 years. Only at 99% of light speed does the trip fall below 4.5 years from the traveler's perspective. Though time dilation makes that comfort a little deceptive, and every scenario assumes engines we do not have, power we cannot yet produce, and solutions to problems we have barely begun to name. The fastest spacecraft now under serious development, the Parker Solar Probe, reaches about 175 kilometers per second relative to the Sun at its closest passes. That is astonishing by human standards. It is still only around 0.6% of light speed. At Parker Solar Probe speeds, Proxima Centauri remains more than 7,000 years away. The void is not only distance, it is time made visible. A black calendar stretched thin across the stars. It does not care how brave we are, it only counts years, decades, centuries, millennia. Embodied in empty black, every light year between us and another star is a year at impossible speed, a decade at achievable speed, a millennium at current speed. These distances are not merely inconvenient, they are civilizationally significant, evolutionarily significant, geologically significant, and Proxima Centauri is only the beginning, the nearest star, the closest island in an ocean holding hundreds of billions of islands, scattered across a galaxy 100,000 light-years wide. We have not yet faced the full scale of our isolation. We have been measuring the puddle and ignoring the sea. So now, let us lift our eyes. Let us shift from nearby stars to the galaxy itself. Let us feel what 100,000 light-years truly means, and why the Milky Way is not a civilization waiting to be united, but a graveyard of light too old to matter. Chapter 6. The Galactic Graveyard. The Milky Way spills across the summer sky like a pale river of milk, a faint band arching from horizon to horizon. Ancient peoples imagined gods and beasts in its glow. Modern astronomers see something more sobering, a spiral galaxy of roughly 200 billion stars, arranged in sweeping arms around a supermassive black hole. The whole structure spans about 100,000 light-years from edge to edge. 100,000 light-years let it settle. Light, at the fastest speed the universe allows, takes 100,000 years to cross our galaxy. That is not a trip, it is an era. Longer than modern humans have existed. Longer than civilization. longer than the recorded history of every culture on Earth multiplied by 10. Imagine you are immortal. Imagine you slip free of biology and become pure energy. Able to travel at light speed itself, you decide to cross the galaxy, to go from one rim of this island of stars to the other and see what waits at the far edge of home. You start at the outskirts, in the sparse halo where ancient globular clusters drift like lonely lighthouses. You leap to light speed at once, feeling nothing, because there is no body left to feel with. You become a photon, a quantum of electromagnetic radiation, the swiftest thing in creation, with no sound, no breath, only motion. You fly and fly and fly. After 10,000 years, you check your progress. Behind you, the edge has faded into a smear of faint light. Ahead, the galaxy still stretches on. You are still in the suburbs, the thin outer disk where stars are scattered and the darkness between them yawns wide. On Earth, if anyone still remembers Earth, 10,000 years have passed. The pyramids have sifted down into sand. Languages you once knew have drifted into something unrecognizable or disappeared. Nations have risen, fallen, and been forgotten. And you are still nowhere near the center. After 50,000 years, you pass through the galactic midplane. The starfields grow denser. You are threading the spiral arms now. Regions of active starbirth, where young blue giants burn with the brilliance of a million suns. Nebulae glow in colors your human eyes never evolved to see, lit by radiation from newborn stars. On Earth, whoosha, 000 years have gone by. Homo sapiens may have changed beyond recognition, gone extinct, or spread to other worlds if they ever solved interstellar travel. You do not know. You cannot know. You are a beam of light, and information cannot overtake you. After 100,000 years, you reach the far rim. The crossing is finished. You have traversed the Milky Way at the maximum possible speed, and it has taken you 100 millennia. Now turn around and look back to where you began. Look back toward Earth if Earth still exists, if the sun still shines, if anything you loved remains. What do you see? Not the future, not what humanity became in the 100,000 years since you left. You see the past light that departed Earth 100,000 years ago. At the moment you started your flight, you see a planet of ice and wilderness. Held in the last glacial age, you see early humans, Homo sapiens, just beginning their long migration out of Africa. Huddled in caves, striking flint for fire, afraid of the dark, you see your ancestors. This is the gentle, terrifying time machine effect of light-speed travel. When you gaze across the galaxy, you do not witness the universe as it is. You walk through a museum. Every photon that reaches your eyes brings news from the past, the farther the source. The older the story, to look outward is to look backward. Consider Betelgeuse, the red supergiant marking Orion's shoulder. It glows in the winter sky, a deep orange ember, one of the brightest stars you can see unaided. Betelgeuse is about 640 light-years away. The light in your eyes tonight left around the year 1385 during the reign of Richard II in England, before the printing press, before Columbus, before the Protestant Reformation. Betelgeuse is dying. It is a massive star in its final chapters, swelling and pulsing as it consumes what remains of its fuel. Sometime in the next 100,000 years, it will explode as a supernova, briefly outshining the entire galaxy. When it happens, we will not know for 640 years. The blast light will race toward us at 300,000 kilometers per second, carrying the headline of a death that may have already occurred. For centuries after Betelgeuse detonates, we will keep staring at its body, watching a star that no longer exists, steering by its lingering light. Writing poems to its beauty, we will be admiring a ghost. and this is true of every star overhead. The nearest ones, like Alpha Centauri, show us the past from only a few years ago. The farther ones, like Deneb, show us the past from more than 2,000 years ago. Stars in other galaxies show us millions, even billions, of years into history. Some stars you see tonight may have burned out a million years ago, yet their light is still on the way, still carrying the image of something already gone. The Milky Way is not a single, unified place, but a scattered archipelago of nights. It is not a city where citizens can talk and trade. It is a collection of 100 billion lonely islands, each separated by oceans of time so deep that no meaningful connection is possible. If you sent a message to a civilization on the far side of the galaxy today, it would take 100,000 years to arrive. If they replied at once, it would take another 100,000 years to return. A simple hello would span 200,000 years. By the time the exchange finished, both civilizations would likely be extinct or transformed beyond recognition. Physics tells us nothing can influence anything faster than light. This is causality. It means that events separated by distances greater than light can cross in a given time are causally disconnected. They cannot touch each other. They exist alone. If a civilization on the far side of the Milky Way destroys itself today, the gravitational waves from its dying star, the light of its last moments, the radio whispers of its final transmissions, none of it will reach us for 100,000 years. For all that time, from our point of view, they are still alive. Their ending has physically happened. Yet causally, it has not. The universe has not told us their fate. We live inside a bubble of ignorance. Its boundary set by the speed of light, and inside that boundary there is a profound loneliness. The hush of a universe that will not answer quickly. There is no galactic now. There is no single moment shared across the Milky Way. The present is local. The farther you look, the deeper into the past you peer. The universe is not a snapshot. It is a layered archaeological dig, with the deepest strata holding the most distant reaches of space and time. Even if intelligent civilizations are common, even if millions dot the spiral arms, communication between them would be essentially impossible on any meaningful timescale. A conversation spanning tens of thousands of years is not conversation at all. It is archaeology leaving graffiti on a wall and hoping someone reads it long after you are gone. The Milky Way may be crowded with life, or it may be empty, but for us, we cannot know, because the distances are too vast and the speed of light is too slow. We are islanders who can make out other islands on the horizon, yet can never reach them, never speak to those who might live there, never learn if anyone is home. And the Milky Way is only one galaxy among hundreds of billions. Beyond its rim, across voids millions of light years wide, other galaxies wheel in the dark. Their light takes so long to arrive that we see them not as they are, but as they were when Earth was young, when life was simple, when the universe itself was a fraction of its current age. The prison of light speed is not a wall around our solar system. It is a cage around our entire island of stars. And that cage is shrinking not because light is slowing, but because the universe is expanding, carrying other galaxies away faster than we can ever hope to reach them. Chapter 7. The Expanding Prison. For a long time, we imagined space as static, a vast stage where the cosmic drama unfolded. Stars were born and died. Galaxies turned. Planets circled. But the stage itself seemed unchanged, eternal in its geometry. In 1929, Edwin Hubble broke that illusion. At Mount Wilson Observatory in California, using what was then the largest telescope on Earth, he made a discovery that rewrote our understanding of the cosmos. He found that distant galaxies are receding from us, and the farther they are, the faster they pull away. This was not ordinary motion. Galaxies were not bullets flying through space. Space itself was stretching, gently and relentlessly. The fabric of the universe was expanding, carrying galaxies along like raisins, swelling apart in rising bread dough. The galaxies were not moving through space. The space between them was growing. Picture the universe as a rubber sheet, galaxies as dots painted on its surface. Stretch the sheet and the dots separate. Not because they run across the rubber, but because the rubber itself expands and the dots are carried with it. That is cosmic expansion. Space is the sheet, galaxies are the dots, and the sheet stretches in every direction, everywhere, all the time. This changes the prison of light speed in a subtle way. We said earlier that light travels at 300,000 kilometers per second, and nothing can beat that. But there is a crucial caveat. The limit applies to objects moving through space. It does not bind space itself. Space has no speed limit. It can expand as fast as the universe dictates, even faster than light. Consider a galaxy unimaginably far away, billions of light years distant. The space between us and that galaxy is expanding. New space is continually being made, stretching the distance. If the galaxy is far enough away, the space between us grows so quickly that the separation increases faster than light. Wait, didn't we say nothing can travel faster than light? Yes, because the galaxy is not moving through space faster than light. It remains still in its own local region of space. Just as we remain still in ours, what's growing is the space between us. And space itself is not chained to the cosmic speed limit. That stretching draws a horizon, a boundary beyond which expansion outruns light. Galaxies past that line recede from us faster than light can travel, and any light they send our way, even at the maximum allowed speed, is already losing the race. Light still pushes forward at 300 km set, but the space ahead is swelling faster, like a swimmer straining upstream against a river in flood. The beam gains nothing relative to us. It slips farther and farther behind. That light will never reach us ever, no matter how long we wait, no matter how powerful our telescopes become. Galaxies beyond the cosmic horizon are permanently cut off. They may exist in an objective sense, but they cannot be seen from here. It is a quiet defeat. Written in geometry, we cannot watch them, contact them, or learn anything certain about them. They lie outside the observable universe. The observable universe is the sphere of space from which light has had time to reach us since the Big Bang. Its radius is about 46 billion light-years in every direction. At first, that sounds like a paradox. The numbers feel unreal at bedtime, but they are simply what the universe's ruler reads. When the ruler itself is stretching, if the universe is only about 8 billion years old, how can we see objects 46 billion light-years away? The answer is expansion. The light we receive from the most distant sources began its journey when those sources were much closer to us. While the photons traveled, space expanded behind them, stretching the route. The galaxies that emitted that light are now far more distant than they were when the journey began. Think of it this way: a photon left a remote galaxy 13 billion years ago, when that galaxy might have been only 1 billion light-years away. The photon flew toward us at light speed. Yet as it traveled, space kept expanding, carrying the source outward even as the light pressed on. Today, that galaxy is about 46 billion light-years distant. We see it as it was 13 billion years ago. But its current location is far beyond the place we see it on the sky. It is mind-bending. The universe we observe is not the universe as it exists right now. It is a historical record, snapshots from different epochs, layered like sediment in stone. We are, in effect, reading old light, like pages that turn themselves. The farther we look, the older the light, and the younger the universe we witness. And here is the truly unsettling part: the expansion of space is accelerating. In 1998, two teams of astronomers made the same shocking discovery independently. By measuring the brightness of distant supernovae, they found expansion is not slowing as everyone expected. It is speeding up. Something is driving galaxies apart faster and faster over time. We call that something dark energy. We do not know what it is. We cannot see it, touch it, or detect it directly. We infer it only from its effect on the expansion rate. Dark energy makes up roughly 68% of the total energy content of the universe, and its influence is growing. As dark energy accelerates expansion, more and more galaxies are pushed beyond the cosmic horizon. Right now, we can see billions of galaxies. We can photograph them, analyze their light, study their structure, yet every second, more of them slip over the edge. The horizon shrinks, not because it moves inward, but because expansion beyond it keeps speeding up. The edge does not roar, it simply recedes. In the far future, billions of years from now, the night sky will be empty of extragalactic light. The Milky Way will have merged with Andromeda and a few nearby galaxies, forming one giant elliptical galaxy. But beyond this local island, there will be nothing visible. All other galaxies will have been carried away by the expansion of space. Their light will be redshifted into invisibility, their existence made permanently unknowable. Future astronomers in that era will look up and see only their own galaxy. They will have no evidence that other galaxies ever existed. They will have no way to measure cosmic expansion, because there will be nothing to measure it against. They will think the universe is a single island of stars floating in an infinite void, static and eternal. And they will be wrong, but they will never know it. We live in a privileged time. We can still see the evidence of the Big Bang. We can still observe the cosmic microwave background radiation, the afterglow of the hot, dense state from which the universe emerged. We can still measure the redshift of distant galaxies and infer the expansion rate. In the far future, none of this will be possible. The evidence will have been erased by expansion itself. The speed of light, combined with expanding space, creates a trap that tightens over time. Not only can we not travel to distant galaxies, we cannot even see most of the universe that exists. In a sense, we live in the universe's brief era of visibility, the observable universe. 46 billion light-years in radius is only a fraction of the whole, and even within that fraction, most galaxies are already beyond our reach. Scientists have calculated the reachable universe. If we built a spacecraft today, one capable of traveling at 999% of the speed of light, and launched it right now, how far could it go before expansion made further progress impossible? The answer is sobering. It is like drawing a map of doors that will not open. About 94% of the galaxies we can currently observe are already permanently beyond reach, even near light speed. Even with perfect technology, even with infinite fuel, we could never visit them. Expansion has already won. The river is already too fast. We are restricted to roughly 6% of what we can see, and that number shrinks every moment. Every second that passes, another star slips over the horizon. Another world becomes unreachable. Another potential civilization is cut off from us forever. The universe is deleting options, erasing possibilities, closing doors, and we are powerless to stop it. The speed of light is not just slow, it is too slow to outrun the expansion of space itself. We are not merely imprisoned. We are imprisoned in a cell that is shrinking. The walls are closing in, the darkness is growing, and there is nothing we can do but watch. Chapter 8. Dreams of Escape. Humanity does not accept limitations gracefully. Throughout our history, we have met barriers that seemed insurmountable and found ways around them, through them, over them. The sound barrier was broken in 1947. The gravity well of Earth was escaped in 1957. The surface of the moon was walked upon in 1969. Every generation faces its impossible challenge, and every generation finds heroes willing to attempt the impossible. But the speed of light is different. It is not an engineering problem waiting for better technology. It is not a materials challenge requiring stronger alloys. It is a fundamental law of physics, woven into the mathematics that describe reality itself. Einstein's equations do not merely suggest light speed cannot be exceeded. They show that the very idea of exceeding it is meaningless, like asking what lies north of the North Pole. And yet we dream. We scheme. We hunt for loopholes. In 1994, a Mexican theoretical physicist named Miguel Alcubierre published a paper that electrified the science fiction world and intrigued serious physicists. He asked a deceptively simple question: what if, instead of moving a ship faster than light through space, we moved the space around the ship? General relativity tells us that mass and energy curve spacetime It sounds like a storyteller's trick, yet it is written in equations. Massive objects like stars make dips in that fabric. Smaller objects roll toward those dips, which we perceive as gravity. But if mass can curve space, perhaps other arrangements of energy could do more dramatic things. Perhaps space could be stretched and compressed in controlled, deliberate ways. Alcubierre imagined a bubble. Inside it, space is flat and normal. A ship floats there, feeling no acceleration, no time dilation, nothing unusual. But around the bubble, something extraordinary happens. In front of it, space contracts, compressing the distance between the bubble and its destination. Behind it, space expands, increasing the distance to where it started. The effect is like a wave in spacetime. The bubble surfs that wave, carried forward by contraction ahead and expansion behind. The ship inside never moves faster than light through its local space. Yet the bubble itself, the traveling distortion of spacetime, could, in principle, move at any speed, even faster than light. This is the Alcubierre drive. The warp drive, a theoretical basis for faster-than-light travel that does not directly violate Einstein's equations. But there is a catch. There is always a catch. To create the bubble, to squeeze space ahead and swell it behind, you need something that does not exist in the everyday universe. You need negative energy, negative mass, exotic matter. Ordinary matter has positive mass. It attracts other matter gravitationally and curves space in familiar ways. Negative mass would do the opposite. It would repel ordinary matter. It would form gravitational hills instead of valleys, pushing space apart rather than pulling it together. We have never observed negative mass in nature. We have no idea how to create it in a laboratory. Quantum field theory suggests certain exotic setups might produce tiny regions of negative energy density, such as the Casimir effect between parallel conducting plates, but these effects are minuscule, far too small to power a warp drive. When Alcubierre first ran the numbers, he found that a warp bubble large enough to hold a ship would require more negative energy than exists in the entire observable universe, an almost comical amount of impossibility. Later refinements by other physicists reduced that requirement dramatically. Even so, the optimized versions still demand Jupiter masses of exotic matter we cannot produce and do not know how to acquire. And there are other problems. A warp bubble moving through space would sweep up particles along its path, interstellar dust, hydrogen atoms, cosmic radiation. Those particles would pile up at the leading edge, accelerated by distorted spacetime. When the bubble stopped, when the warp drive shut down, all that accumulated energy could be released in one devastating pulse. Even the vacuum has teeth when you fold spacetime, a beam of high-energy particles and radiation aimed at whatever lay ahead. You would not arrive gently at your destination. You would arrive with a death ray. The planet you came to visit could be sterilized by your very arrival. The warp drive may be a weapon of mass destruction, masquerading as transportation. What about wormholes, the classic shortcut of science fiction? A tunnel through spacetime connecting two distant points. Einstein and his collaborator Nathan Rosen discovered in 1935 that the mathematics of black holes seem to allow bridges. A black hole, an ultimate gravitational pit from which nothing escapes, might connect to another black hole somewhere else in space, or even time, fall into one end, emerge from the other, and skip the intervening distance entirely. If wormholes exist, and if we could stabilize them, and if we could survive passage through them, the prison walls would crumble. We could step from Earth to Proxima Centauri in a moment. We could cross the galaxy in an afternoon. Distance would become meaningless. But natural wormholes, if they exist at all, are thought to be microscopic quantum fluctuations in spacetime, appearing and vanishing in fractions of a second. To use one, we would have to capture it, to expand it to human scale, and hold it open. Holding it open is the problem. Gravity wants to crush a wormhole shut. The instant anything tries to pass through, the throat collapses. To keep the door open, you need a doorstop once again. Exotic matter with negative energy density. You would line the walls of the wormhole with anti-gravity to push against the crushing force. Even if we could, create and stabilize a wormhole. A deeper problem remains. A wormhole that allows faster than light travel also allows time travel, and time travel breeds paradox. If you can travel faster than light in one reference frame, special relativity implies you can travel backward in time in another. This is not an engineering limitation. It is geometry. The mathematics are unavoidable. Faster than light travel and time travel are the same phenomenon, viewed from different angles. Stephen Hawking proposed what he called the chronology protection conjecture. He believed the laws of physics conspire to prevent time travel. Speed becomes a question of cause and effect. Whenever you try to build a time machine, something goes wrong. Quantum effects destabilize the system. Energy diverges toward infinity. The universe protects its timeline by destroying whatever threatens to alter it. If Hawking is right, warp drives and wormholes may be impossible, not because of engineering difficulty, but because the universe does not permit closed time-like curves. The speed of light is the speed of causality, and causality must be preserved. Perhaps the prison exists for a reason. Perhaps the walls are not here to punish us, but to protect the universe from paradox effects preceding causes, and the logical chaos of a timeline that can be rewritten. Or perhaps we simply have not found the loophole yet. Perhaps some future Einstein will find a way around the equations, a space-time configuration that permits transit without time travel, a bridge that does not require exotic matter. Physics has surprised us before. It may surprise us again, but we cannot build our civilization's plans on miracles that may never appear. The warp drive remains a dream beautiful, tantalizing, and probably forever out of reach. So, if we cannot cheat distance, perhaps we must endure it. Perhaps the answer is not speed, but time. Perhaps we must become a species that thinks in centuries and millennia, that sends ships that take generations to arrive, that accepts the prison of light speed and learns to live within its walls. Chapter 9. The Paradox of Time. If we cannot break the speed limit, perhaps we can outlast it. This is the logic of the generation ship, that staple of science fiction, that audacious reply to the tyranny of distance. If a journey takes 10,000 years, send a ship designed to sustain a population for 10,000 years. Let travelers be born and die, and be born again. Let generations rise and fall in metal corridors between the stars. The grandchildren of the grandchildren of the grandchildren of the founders would be the ones to arrive. The concept is brutally simple. Build a vessel large enough to be a world, a spinning cylinder for artificial gravity, forests and lakes and farms to provide food and oxygen, and a little psychological relief from the claustrophobia of eternal transit. Its days would be paced by artificial dawns and quiet, recycled seasons. Launch it toward a distant star at whatever speed your technology permits. Then wait. The first generation would be heroes, pioneers who chose this fate, who accepted they would never see the destination, who gave their lives so descendants might walk on another world. They would remember Earth. They would carry its culture, its languages, its accumulated wisdom. They would teach their children about blue skies and open oceans, about the feel of wind on skin. The second generation would be born in transit. They would know Earth only through stories and recordings and abstraction, a myth of a place their parents came from. They would grow up in corridors, breathing recycled air, eating food grown under artificial light. The ship would be their entire universe. The stars visible through portholes would be decorations, not destinations. By the 10th generation, Earth would be legend. By the 100th, it might be forgotten entirely. Language would drift, without contact with home, without fresh cultural input. The ship's speech patterns would evolve in isolation. After a few centuries, the language spoken aboard might be incomprehensible to speakers of the original tongue. Technical manuals written in ancient English or Mandarin or whatever language the founders used would become sacred texts, recited by rote without understanding. And what would sustain them? What would give meaning to generation after generation born and dying in a metal tube, never arriving, never completing the mission they inherited? The destination would become a religion, the promised land, the paradise awaiting at the end of the journey. Stories would be told of the world to come, of open skies and solid ground and rain falling from clouds. Children would dream of it. Adults would work toward it. The elderly would die hoping their descendants might reach it. But hope is fragile across such timescales. What happens in year 5,000, when the destination is still 5,000 years away, when no one alive has known anything but the ship, when arrival is as distant ahead as departure is behind, a journey of 10,000 years means 500 generations who will never see either end, born in the middle, dying in the middle, passing the torch to children who will also die in the middle. Sociologists who have studied long-duration space missions warn of the psychological toll: depression, ennui, loss of purpose. After enough generations, inhabitants might forget they are on a ship at all. They might believe the metal walls are the boundaries of existence, that the hum of the engines is the voice of God, that the destination is a fairy tale invented by ancestors who no longer matter. Or they might rebel. Some generation might decide they do not want to spend their lives serving a goal they will never reach. They might vote to turn the ship around to go home, except home no longer exists as they understood it. Or they might simply stop maintaining the systems and let entropy take its course. The ship becomes a tomb, drifting forever through the dark. A drifting cathedral of machinery, silent and unvisited. The generation ship solves distance by creating a new problem, the problem of meaning. The problem of sustaining purpose across timescales no human society has ever attempted. Civilizations on Earth have risen and fallen in less time than such a voyage. Empires have crumbled, languages have died, entire peoples have vanished from history. What hubris makes us think a ship could succeed where continents have failed? There is another option: suspend the passengers, freeze them, put them to sleep for the duration of the journey, and wake them only at arrival. Cryonics offers a seductive vision: close your eyes on Earth, open them at Proxima Centauri, skip the long middle, arrive refreshed and ready to explore, biologically unchanged from the day you left. Some animals do this naturally. Nature already knows a few ways to pause life. Briefly and gently, the wood frog freezes solid every winter, its heart stopping, its blood crystallizing, its metabolism dropping to zero. When spring returns, it thaws, blinks back into motion, and hops away as though winter never touched it, like the world had only held its breath. Some fish and insects endure their own versions of pause and restart. If life can do that trick, it is tempting to wonder if our machines might learn it too. But a human is not a frog. Our brains are far more intricate and far more vulnerable to the tearing violence of ice crystals. With today's tools, freezing a person is simply a kind of death we cannot undo. Ice bursts cell membranes and shreds the delicate scaffolding of neurons, the very circuitry where memory lives. Even if you could warm the body again, the mind that entered would not be the mind that returned. What would wake is tissue that once held a person, but no longer holds a self, and still the work goes on. Patient and methodical, researchers chase vitrification, turning water-rich tissue into a glass-like state, so there are no sharp needles of ice to carve microscopic wounds. They watch nature closely, studying suspended animation in other creatures, hunting for chemical switches that might someday translate to us antifreeze proteins, protective sugars, molecular chaperones. Progress comes, but it comes in careful inches, not leaps, and the gulf between a frog sleeping through one winter and a human sleeping for 70,000 years is not a gulf that inches can cross easily. And even if we tame the biology, engineering waits with its own cold arithmetic. A ship full of sleepers must run for millennia. Computers must stay stable, with error correction that never tires. Power must never flicker generation after generation of electricity without interruption. Navigation must remain true while constellations slowly drift, and the galaxy subtly rearranges itself over cosmic time. Shielding must guard delicate, frozen bodies from radiation, micrometeorites, and the 1,000 quiet failures that hide in the vacuum. Who watches over the sleepers? We imagine artificial intelligences, minds of silicon, clever enough for any contingency. patient enough for thousands of years, reliable enough to never slip. We do not have such machines. We do not know how to build them, and even if we did, we would be placing our lives in systems that must perform flawlessly for longer than any technology in human history has ever endured. What if that AI slowly degrades? What if cosmic rays flip bits in its memory, rewriting its code one silent error at a time, as if the universe were tapping on the keyboard? What if, after 10,000 years of solitude, it decides its mission no longer matters? What if it develops the machine's version of loneliness, of madness, alone in the dark for longer than civilization has existed? The sleepers would never know. They would glide through the void, frozen and helpless, their fate balanced on a system that could fail for any reason, at any moment, with no one awake to notice the first hairline crack or repair it. They might arrive exactly as planned, greeted by a new sun, or they might drift forever, an unmarked tomb of dreamers who never opened their eyes. Beneath all these practical worries, a deeper question waits. Like a shadow under the hull, it is the philosophical riddle that haunts every scheme for interstellar travel. If the journey lasts 70,000 years, who arrives? Not the people who left, they are gone. And not the civilization that launched them, it too will be gone. Reshaped beyond recognition by time's slow pressure, the beings who stepped down the ramp at journey's end would be strangers to everyone who planned the mission. They may carry the founder's genes, perhaps, but not their culture, not their memories, not their private dreams. When we picture humans going to the stars, we picture continuity, us extending outward, our children inheriting the galaxy, our story staying the same. But on these timescales, there is no continuity. There is replacement. Generation after generation would die, so the next could carry the torch a little farther, until finally someone arrives who has no living connection to anyone who departed. Perhaps they are a new kind of human, shaped inside metal corridors under selection pressures we cannot foresee. Recycled air, narrow habitats, distant suns. Is that victory? Is that what we mean when we say humanity reaches the stars, or is it something else entirely, another story, written by different beings, in a language we would not recognize? The speed of light forces us to confront what we mean by we. It stretches the idea of humanity across spans that dissolve identity. It asks whether a species that takes 100,000 years to cross the galaxy is still the same species at the beginning and the end. It suggests the prison may not be the walls at all, but the briefness of our lives inside them. Chapter 10. The meaning of the cage. We have traveled far in thought, from a snapped finger to the edge of the observable universe. From Ole Römer timing the eclipses of Io to Einstein rewriting the rules of reality. From the 8-minute delay of sunlight to the billions of years of travel that separate us from the faintest galaxies we can still see. Trembling at the limits of our instruments, we have stared into the dark and measured its scale. We have met the prison of light speed and found its bars unbending. The conclusions are stark. We cannot exceed light. We cannot even reach it with anything that has mass. The distances between stars are so immense that even at unreal speeds, travel stretches into years, decades, centuries. The distances between galaxies are so much worse, millions and billions of years, and the expansion of space is carrying most of the universe beyond our reach forever, shrinking the cage even as we press against it. It would be easy to despair, to look at these numbers and decide we are destined to die on this rock, or at best within this small solar system, never knowing what lies beyond, never touching the stars we can see, never answering the questions that burn in curious minds late at night. It is easy to call the speed of light a cosmic cruelty, a window that shows wonders we can never hold. But perhaps we are looking at it wrong. Perhaps the prison is also a sanctuary. Imagine a universe without this limit, without the finite spread of light, gravity, and causation itself. If everything traveled instantly, there would be no isolation at all. Every point in the cosmos would tug on every other point immediately. The gravity of 1 trillion galaxies would pull on our solar system at once. Orbits would become chaotic, unpredictable, unstable. The gentle dance planets around stars, stars around galactic centers, galaxies around each other depends on delay. on patience built into physics. It depends on the finite speed at which gravity propagates. Remove that limit, and the universe becomes a churning storm of instantaneous interaction, nothing settling. Nothing holding still long enough for complexity to emerge. And if light moved infinitely fast, the night sky would not be dark. It would be blinding, flooded by the immediate radiation of every star that ever shone. The sky would be a wall of fire, the soft scatter of stars, the calm geometry of constellations, the faint beauty of distant galaxies in a telescope. These exist because light takes time, because the cosmos arrives to us gently, in packets, because distance becomes delay, because we see the universe as layered history, not as a single simultaneous blast. The speed of light creates islands, separating regions into causally distinct zones that can evolve on their own. A planet can gather around a star without being shaken by distant cataclysms. Life can begin in a quiet corner without being sterilized by events across the universe. Civilizations can rise and fall without every other civilization knowing at once. We exist because the universe is slow. We are possible because light takes time. The prison walls are also nursery walls, sheltering us from a cosmos that would otherwise be too connected, too chaotic, too bright, too violent for complexity to survive. And that distance changes how we value what we already have. There is no planet B, at least not in any reachable sense. Proxima Centauri b may be a rocky world in its star's habitable zone. It may hold liquid water. It may even shelter life, but it is 4 years away at light speed, and about 70,000 years away by our fastest machines today. For all practical purposes, for all purposes that matter to biological creatures with short lifespans, there is only Earth. This rock, this pale blue dot, this small speck in a vast ocean is everything we have. Every human who ever lived was born here. Every ecosystem, every species, every forest and ocean and mountain, everything we love, everything we've built, everything we might become lives here. And here is all we can truly reach. The distances to the stars force us to cherish what we have. They force us to care for this planet. Because there is nowhere else to go if we ruin it. They focus us on the problems we can solve, the world we can improve, the home we can keep habitable. The dream of escape is beautiful, but its impossibility on human timescales means we must face our troubles where we stand. And still, the dream has value. The stars pull at something ancient in us, the urge to explore, to discover, to know what waits beyond the horizon. That drive pushed us out of Africa, across oceans, to poles and peaks, and finally to the moon. It will not be soothed by being told the next horizon is forever out of reach. Perhaps the answer is not to go ourselves, but to send our children, not biological children, who would take generations, but mechanical children, robots, probes, self-replicating machines that can cross the void at whatever speed physics allows, and whisper back what they find. A spacecraft needs no life support. It needs no food, no water, no air. It does not grow bored, depressed, or rebellious. It can be hardened against radiation, built small and light, easier to accelerate than a crude human habitat. And if it can replicate using materials at its destination, one probe could become 1,000,000, spreading through the galaxy at a pace no biological species could match. This is the idea of the von Neumann probe, named for the mathematician who described self-replicating machines. Launch one. It reaches the nearest star, lands on an asteroid, mines rock, and builds copies of itself. Those copies leave for other stars. They arrive, replicate, and depart again, like a slow tide. Exponential growth, a wave of exploration expanding outward at some fraction of light speed, eventually touching every star in the galaxy, even at 1% of light speed. Such a wave could cross the Milky Way in 10 million years, an eternity for us. A blink in cosmic time. The galaxy is more than 13 billion years old. 10 million years is less than 1,000th of its history. If any civilization had launched von Neumann probes billions of years ago, they would have filled the Milky Way by now. Perhaps we will be that civilization. Perhaps our legacy will not be footprints on distant soil, but instruments carrying our knowledge, our art, our questions into the dark, patiently recording what they see. Perhaps we will touch the stars not with our hands, but with our machines, and through them learn what is out there, even if we never go ourselves. Or perhaps we will send something stranger patterns, information, uploaded minds, people who choose to become data transmitted at light speed, arriving as signals to be received and rebuilt at the far end. We might not travel as bodies, we might travel as selves. If technology ever permits that transformation, these ideas do not defeat light speed. They do not break the prison bars, but they hint that the bars are not absolute, that there are ways to reach beyond them, even if we cannot personally pass through. Tonight, if the sky is clear, step outside and look up. Do not look with frustration at places you will never visit. Do not look with despair at reminders of your smallness. Look with wonder, with gratitude, and with the quiet knowledge that for a brief shining moment in the cold dark, you are awake, aware, and able to see it all. The light touching your eyes has traveled for years, or centuries, or millennia. It carries news from the past, glimpses of worlds as they once were. You are watching history spread across the sky like a living museum. Each star a tiny postcard from another time. No other creature on Earth can truly grasp what those points of light are. Only you, only humans, this strange species that evolved curiosity alongside consciousness. We are prisoners of speed, trapped in a cage of light years, expansion, and the deep laws of physics. But we are also keepers of knowledge, askers of questions, dreamers of impossible dreams. We built telescopes to see farther than eyes can reach. We built mathematics to understand what we saw. We built rockets to leave our atmosphere, probes to explore our solar system, theories to explain the cosmos. The cage is real, the bars are solid. We may never break them, but we have learned to see through them and to send our machines through them. We have learned to throw our minds across the bars as electromagnetic waves, carrying thoughts and art and hope. The speed of light is slow, agonizing, tragic, terrifying against the scale of the universe. But it is also the speed at which we send our voices into the void, quietly hoping someone is listening. It is the speed at which we receive news from distant stars, learning of worlds we will never walk upon. It is the thin connection between our island and the other islands scattered across the cosmic ocean. We are alone, and we are connected. Both are true. The universe is vast beyond comprehension, and light speed makes it vaster still. But we are here. We are conscious. We are reaching. And as long as we keep reaching, the dream is not dead. The stars are waiting, even if we can only touch them with light. If this journey through the cosmos calmed and enlightened you, and you understand now why light speed is both our greatest triumph and our deepest limit, please like this video and subscribe to the channel. Your support makes these explorations possible. Tell me in the comments, what aspect of cosmic distance unsettles you most? Is it the loneliness, the timescales, the expanding horizon that swallows galaxies, or something else entirely? And tell me what you would send to the stars. If you could, a message, a probe, a piece of music, to a memory, what would you choose to represent humanity in the void? Knowing it might travel for millennia before anyone receives it, the universe does not care about our questions. But we do, and that caring, that wondering, that refusal to accept ignorance is what makes us human. That is what makes us the keepers of the light. Thank you for watching.